All right, so today's topic is sort of, I never quite know what to call it, but sort of miscellaneous mathematical tools that are built into MATLAB that you'll find very useful in the future, but that didn't really fit into the main flow of the course. Since this is a programming course, we don't really focus much on doing numerical computations using the built-in capabilities. We have you do everything from scratch with programming. But in the future, as you're using MATLAB in your advanced courses, it doesn't really make any sense in many cases for you to write, say, a discrete time simulation from scratch when there are built-in functions to do some of these things for you. So I just want to acquaint you with some of the capabilities that are built in that you'll find very useful in the future for doing different kinds of numerical computations, starting with curve fitting, interpolation, which we've already seen, but we're going to revisit that. Probably the most useful thing you can do with MATLAB that'll really save you a lot of work in your future coursework is knowing how to solve a system of linear equations. In many of your courses like mechanics, circuits, whatever it is, you analyze the system, you end up with 3 or 4 equations and 3 or 4 unknowns, and you've got to solve them. And that's really tedious if you have to do it by hand, but I'll show you how to do that in MATLAB very easily. And then kind of advanced topics, which are optional. They're not required for this exercise. They're extra credit problems. Knowing how to use it to solve ordinary differential equations, which is the other really fundamental thing that you'll do a lot of in your advanced courses. And then optimization and parameter estimation. And so since these last 2 things are optional, what I want to do is just go through the first 3, then let you work on the exercise. And then the last 15 minutes or so of class, I'll go over the last 2 topics. And if you're interested in doing those to try to get the extra credit, you can work on them on your own. All right, so the first thing is curve fitting, or what's called in Excel, adding a trend line. Same basic thing. And I'll show you how to do a polynomial. If you want to do something other than a polynomial, more advanced techniques are needed, but MATLAB has a built-in function called polyfit to do any kind of polynomial curve fitting very easily. So what I'm going to do as an example here is just a straight line fit, revisiting something that you learned back in 1181 in the beam bending lab, and some of you have probably seen it again in mechanics of materials. That's deflection of a cantilever beam. So you might remember in 1181, you took data where you measure the deflection of a beam for different loads. So P is the load, delta Y is the measured deflection. And the other numbers are just parameters, characteristics of that beam. Its length, the elastic modulus of the material, and the area moment of inertia of the beam. And for a solid rectangular beam, the area moment of inertia is 1/12 the width times the height cubed. Now, if you think of this in terms of fitting experimental data, okay, you make a bunch of measurements of delta Y versus P. If you plot that, the slope should be L cubed over 3EI. Right, so that would be the slope. So if you take data, which we're giving you here, simulated data, delta Y versus P, if you fit a straight line to that, the slope should be L cubed over 3EI. So you get that slope, and then you rearrange this equation to solve for E, to get the elastic modulus of the material. All right, so how do you do that in MATLAB? So you use the function polyfit. You give it 3 things: the X data, which in this case is the load, P, the Y data, delta Y, and then what order of polynomial do you want? In this case, we want a straight line, so that's a first order polynomial. In the exercise, we're going to have you do a quadratic, so this will be a 2 instead of a 1. And what this will give you is the coefficients of the polynomial. So let's go ahead and run this, see what we get. All right, so we get these 2 numbers, and you just have to know what order it's giving them to you in. They're in decreasing order. So the first number is the linear term. The second one is the constant term. I said, so when you do a quadratic in the exercise, it'll be the quadratic coefficient first, then the linear one, then the constant. All right, so the slope is this first coefficient. All right, so this first one is the slope, the second one's the intercept. Now let's say we wanted to actually draw the trend line through the data. There's another function you can use called polyval, where you give it those coefficients that you got from polyfit and the set of x values that you want. In this case, I'm just using the same set of load values. And it'll calculate the y values of the best fit line. Okay, so then you can plot the original data, say with an asterisk, and then the fitted line on the same graph. And that's what you get. Okay, so polyval gives you the coefficients of the best fit line, the least squares line. And then I may have said that backwards. Polyfit gives you the coefficients. Polyval then actually gives you the values of that curve. All right, then if you want to, let's say, extract the Young's modulus from the slope, well, the slope is the first coefficient. So I pull out the first element of that coefs array. And then I rearrange this equation to solve it for E. So it's going to be L cubed over 3 times the slope times I. And that's the Young's modulus. All right, any question about that? All right, so that's curve fitting in MATLAB with polyval and polyfit and polyval. So this example, this is actually the same problem that's in the exercise. So I'm not going to do it now, just do it in the exercise. But let's say now we want to do a quadratic. Okay, let's say we measure the position versus time of a projectile. And you know, from basic physics, if it's a constant acceleration, so if we're neglecting drag, for instance, it should follow this equation. All right, so we do a quadratic fit. So you're going to do polyfit again. Okay, something just like this. Oops, wrong one. Polyfit like this. But now instead of order 1, it's going to be order 2 because we're doing a quadratic. And then it asks you to get the acceleration. I'm sorry, not the acceleration. The A. No, that is the acceleration. I'm sorry. The acceleration and the initial velocity. Okay, so keep in mind, you got the coefficients of this equation. And those coefficients are going to be actually in the opposite order they're shown here because it goes in decreasing order of the polynomial term. So the first coefficient is going to be 1/2 A. Right? So to get A, you take that first coefficient, you multiply by 2. And then the second coefficient is just the initial velocity, which is what we're asking for. Okay. All right, so use polyfit to fit a quadratic of this data, extract those first 2 coefficients to get the acceleration and the initial velocity.